Georgios Batzolis will talk about a very interesting looking presentation on score-based Pullback Riemannian geometry, extracting the data manifold geometry using anisotropic flows.
Hello everyone. I think my talk is going to deviate a bit from the main topic of the workshop, but hopefully I can make it interesting for you. Also, especially after a very tiring day. Today I'm going to talk about the manifold hypothesis, which is very prevalent in machine learning in general, and the manifold hypothesis says that general real data distributions tend to lie on lower dimensional manifolds, and this is one of the core assumptions that has been a cornerstone and for like many algorithms, including dimensionality reduction and so on. And today I'm going to discuss about how we can extract the geometry of the data manifold. So yeah, exactly. So there is the manifold hypothesis, as I described, that real-world data tend to concentrate near a lower dimensional manifold M, which is embedded in the ambient space in RD. And recent work has shown that diffusion models and normalizing flows, basically generative models that work directly on the ambient space. For example, variational autoencoders tend to map a latent data point, a latent sample from like a lower dimensional space to a higher dimensional space, so they contract the dimension. Whereas in diffusion models and normalizing flows, we operate on the ambient space. And it turns out the diffusion models and normalizing flows encode the intrinsic dimension of the data manifold if the data is actually supported on a lower dimensional manifold. And I will describe why in a bit. But the question that we are trying to address in our work is, okay, we know that ambient diffusion models and normalizing flows can encode the dimension, but can we take it a step further and can they encode richer geometric information about the data manifold, such as the geodesics or the intrinsic distance on the manifold, or other properties like the curvature? Or can we do Riemannian optimization on the data manifold? Riemannian optimization on the data manifold means that essentially you find a way to do constrained optimization on the manifold. You start from an initial data point on the manifold, and then you're trying to make tiny steps like that are going to maximize or minimize a particular loss function that is defined on the manifold. And you want to make sure that at every step you remain on the manifold. So for example, I have an example here where on the left you see the standard Moon dataset, and which defines a data manifold. In this example, we have a function f that is basically a quadratic function that is minimized on the point x, and it could also be defined in a way that is only defined on the manifold, but here it is defined everywhere. And we're trying to minimize that function while making sure that the entire optimization path will remain on the manifold. And if we know the geometry of the manifold, that I will explain later what that means, then we can do that. On the right, it is basically the same thing, but in higher dimensions. We are essentially like this trajectory that starts from the initialization on the right corner and ends up very close to x, is essentially the initial image on the left, which is a human face that is not smiling, and on the right is the end of the optimization trajectory, which is a human face that is smiling. And effectively, we are actually doing this by doing Riemannian gradient descent on the human face image manifold. I will describe later how this is done. Another application is that we can extract, as I said, we can extract geodesics. Here, what you see is in the upper image, you can see this is the Utah teapot, and essentially on the left column, we have one endpoint. On the right column, we have another endpoint, and everything in between is essentially the trajectory, the geodesic trajectory that connects these 2 points on the SO3 manifold. And on the bottom, you see it is basically the digit 9, which is rotated for every possible angle. This is an 1D manifold, and we're trying to find the geodesics that connect to different rotations. And in the bottom plot, this is done by a diffusion model, which is used to construct a Riemannian metric that extracts the geodesics. In the upper one, these are the ground truth geodesics. We haven't still managed to make it work for the teapots. It's much harder than it's a very difficult problem actually. So let's start from some foundational insights. So as I said before, the data distribution is supported on a k-dimensional manifold, which is embedded in RD, where k is smaller than d. And in the framework of diffusion models, we start by adding Gaussian noise. And the point is that you add enough noise so that you can corrupt the distribution completely. And then what you do is that you train a score model or a diffusion model that learns this quantity here, the gradient of the log density of the corrupted distribution for all diffusion times from 0 to the terminal diffusion time. And once you learn that, you construct a diffusion model because you can construct the reverse process, which is described by a reverse stochastic differential equation that you solve backwards in time, and that's how you generate new samples and you have a generative model. It turns out that as the diffusion time goes to 0, so essentially as the level of perturbation goes to 0, the score function that you learn becomes asymptotically normal to the data manifold. What I mean by that, we have this visual here, is that at every point on the data manifold, you have the tangent space, which is tangent to the manifold, and the normal space, which is normal. And essentially, as the diffusion time goes to 0, if you have an initial data point on the manifold and you perturb it a little bit, and you compute the score function at the perturbed location, you will see that the score function, which is a vector, will lie almost exclusively on the normal space. And it will have a very, very small projection to the tangent space compared to the projection on the normal space. It will have a tangent projection, but as the diffusion time goes to 0, the ratio of the two, basically the ratio goes either to infinity or to 0, depending on how you put them in the denominator or numerator. Yeah, please.
So is this in a high data sampling limit?
Yes, exactly. So we're making the assumption that the score function learned by the neural network, approximates the true score function at some arbitrarily small distance epsilon in L2 norm. So yeah, I mean that is fundamentally a result about the score function of the distribution. And essentially, provided that you have approximated well enough the score function, then you're going to see this kind of behavior. That the score function will exclusively, like the score vector will be exclusively contained in the normal space as the diffusion time goes to 0. There will be some tangent component, but the ratio of the two goes to infinity. The normal projection over the tangent projection will go to infinity, the magnitude of this projection. This is what we have proven in a previous paper. What this means, another application of this, is that the Jacobian of the score essentially becomes an orthogonal projector onto the normal space of the manifold. It is a consequence of the previous result. So if you have like an ambient vector and just multiply it with the Jacobian of the score function, you will see that it will project it onto the normal space. And what that means about the structure of the Jacobian is that if you do a singular value decomposition to the Jacobian of the score function for very small levels of noise perturbation at any point on the manifold, you will see that it is going to have k very small singular values, and those k small singular values are going to correspond to the tangent space, and the corresponding singular vectors will be an orthogonal basis for the tangent space, and the remaining d minus k, where it is the dimension of the ambient space, is going to be the dimension of the effective dimension of the normal space, and the corresponding singular values are going to be very large. And the singular vectors span the normal space. Here is an empirical example. In this case, we have trained a diffusion model on 3 data manifolds of dimensions 10, 20, and 100, all of them embedded in a 1024 dimensional ambient space. We trained the diffusion model, and then at many points on the data manifolds, we calculated the spectrum of the Jacobian, and this is what we plot here. And as you can see, this is the spectrum these are many spectrums actually overlaid for the 10-dimensional manifold. So you will see, it basically shows exactly the structure, that you have a spectrum collapse at exactly the normal dimension of the manifold. And that's how you can read off the dimension of the manifold from a trained diffusion model. You literally just compute the Jacobian of the score function, you do a singular value decomposition, and you can read off from that the dimension of the tangent space, which is the intrinsic dimension of the manifold. Perfect. So, the conclusion from all of this previous discussion is that the Jacobian of the score function doesn't only reveal the intrinsic dimension, but it also encodes the normal bundle, which is essentially the union of all the normal spaces of all the points on the manifold. And this shows that it gives you much more geometrical information than just the intrinsic dimension. So a natural question is, how can we use it to extract richer geometric properties of the data manifold, such as geodesics and distance?
The question to clarify. So you said that the gradient of the logarithm is, in a way, is zero expectation under the distribution, right? Because that's what orthogonality means. The expectation of it is going to be. But for this to hold, you need conditions on your drift and the diffusion, right? It's not true for every.
Yes, of course. You need assumptions of the data distribution. You need to have connected support. You need to have integrability. You need to have the forward process. You mean also the conditions of the forward process as well? Yes. Yeah. You need all of those assumptions, of course. But these are just the standard assumptions that people make in diffusion models in general. Yes, for example, let's say that you're using this variance exploring SD that just people use, where you just literally have zero drift, and you just add noise basically. It would work with that, and and you also need some assumptions on your data distribution as well. But these are standard assumptions that are also made for diffusion models in general, because if you don't make those assumptions, you also lose reversibility of the forward process as well. Yes, of course. Perfect. Okay, so, sorry. Yes, so the idea in this work is that we're trying to extend the previous insights and try to infer other geometric properties of the data manifold from generative models that have been trained on the data distribution. And the way to do this is to use the machinery of Riemannian geometry. And the straightforward way is to try to construct a Riemannian metric tensor on the data manifold that extracts the data geometry. And what do we mean by that? The idea is that you want to construct a Riemannian metric tensor that makes sure that the geodesics will pass through regions that will be, of course, in the data support. They can, and apart from that, you also want the geodesics between any two data points to pass from high likelihood regions of your data distribution. That's how we define the notion of like trying to find geodesics on your data, because that's how we define it. So let's revisit some concepts from Riemannian geometry very quickly. What is a Riemannian metric tensor? The Riemannian metric tensor essentially gives us a smoothly varying inner product on all the tangent spaces of the data manifold, on the tangent bundle. So at every point on the manifold you have a tangent space, and the Riemannian metric tensor is going to give you an inner product for that tangent space, and that tangent space and that inner product is going to change smoothly as you move along the manifold. And essentially, in different regions of the data manifold, you are measuring distance in a different way. But how that rule changes is in a smooth way. And how we define length is just essentially a length of a curve. Gamma is the integral from the starting point to the end point of the velocity of the curve, as the velocity is calculated at every specific tangent space. And the Riemannian metric tensor describes how you should calculate the velocity of the specific tangent space. And the distance is essentially the minimum of the length functional, and the geodesics are the critical points. In local coordinates, the Riemannian metric tensor can be written as a matrix G, where the ith, jth component of the matrix is essentially the dot product under the metric of the ith and jth basis vectors of your coordinate chart. And then it becomes quite easy to see in matrix form how you compute the dot product between two vectors v and w, and the velocity, or like the norm of any vector under your chosen metric. Once you have constructed all of that, once you have constructed all of that, you can find geodesics between two data points by solving the geodesic ODE. The geodesic ODE, it is a second order ODE, as shown here, that involves these functions, which are n cubed. These are n to the 3 functions, which are called the Christoffel symbols, and they are directly related to the metric that you choose. And essentially, they're related to the inverse of the metric and the derivatives of the metric, so they're computable once you have the metric, and then you construct the geodesic ODE, and you can solve the geodesic ODE as a boundary value problem where you set the two endpoints and you're trying to solve the geodesic ODE, and that should give you a geodesic based on the Riemannian metric that you chose. But that can be actually quite hard to compute, especially in very high dimensions. Hopefully there is the construction of pullback metrics that can make things a bit easier to compute in certain cases. The pullback metric on a manifold M can be defined in the following way. We have a smooth map from manifold M to a manifold N, where N is endowed with a metric Gn. And this is how we are constructing the manifold, the Riemannian metric, the Riemannian metric on the manifold M, and this is what we call the pullback metric. The way we construct it is in the following way. We have point on the manifold M, and we have the tangent space, and we have two vectors V and W, and we're trying to compute the metric. How we're doing this is that we are mapping the point X on the target manifold N, and we're gonna get a point F of P. Let's say that was the original point. And the Jacobian of F is going to map the tangent vectors from the source manifold to tangent vectors on the target manifold N. And essentially, we are computing the metric of the push forward vectors under the metric that we chose for the manifold, for the target manifold N. And essentially, by doing that, you're kind of pulling back the geometry of the N manifold using the map F. And this is written in local coordinates in a much simpler way than the way I described it. It is just the Jacobian of the transformation transpose times the Gn matrix times the Jacobian. And it turns out that many good properties can be derived from if you define your metric in the original manifold in such way. The most important property is that this is a local isometry, and what that means is that if you have a geodesic in the original manifold and you map it with the function f to the target manifold, then it is going to remain a geodesic. And if f is a local diffeomorphism, that is going to be what I said is going to be true in the regions where f is a local invertible. But if f is a global diffeomorphism, this is going to be true everywhere. And this is particularly handy in the cases where we choose the target manifold to be Rd and the Riemannian metric in the target manifold to be the simple the standard Euclidean metric. Because that means that if you map geodesics from the original manifold to the target manifold, they will become straight lines. And that can give you also easy ways to compute geodesics, because if you have 2 points on the original manifold where you chose as your metric the pullback metric, then you can literally just map them using the function f to the target manifold and then compute a linear interpolation there, a straight line. And when you reverse that process, when you take the inverse of f, you're going to get a geodesic back in the original manifold. And that is going to be in closed form. You don't need to compute, you don't need to solve the geodesic OD, which is a big win in practice. So let's try to connect it back to what I said earlier about the structure of the Jacobian of the score function and the fact that the score becomes asymptotically normal to the data manifold. We could try to use as a Riemannian metric the pullback metric of the score function of the distribution. Under assumptions, of course. We have to assume that that the score function S mapping from Rd to Rd is a smooth immersion, that essentially that the Jacobian is invertible at every point. That is an assumption that we have to make in order to be able to define a Riemannian metric. So let's say that assumption holds, then we can define the Riemannian metric essentially in local coordinates as J transpose J. And let's see why this would be a good metric to use. If we remember the structure of the Jacobian of the score function, that has n big eigenvalues that correspond to the normal space and k very small ones that correspond to the tangent space, we can see that if we use this metric, then that metric makes sure that the geodesics will have to lie in the tangent space, so on the data support. Because if you have velocities that are trying to leave the manifold, these velocities that are trying to leave the manifold will inevitably have high projection onto the normal space, and this is going to be magnified a lot by the Jacobian, essentially. And so the minimizers should have as little projection onto the normal space as possible, And this shows that this metric will be able to make sure that the geodesics will lie on the data support. But there are some caveats to that. It's not that simple, actually. It turns out that if you choose this metric, it is very good at extracting local properties efficiently, like the dimension and the Riemannian projection operator, so that you can do Riemannian gradient descent and things like this. But it struggles a bit with extracting global properties, such as geodesics and distance. Because what you can do is that you can use this metric and plug it in the geodesic OD, compute the Christoffel symbols, and then try to solve it. And you will see very quickly that, first of all, this is computationally very expensive because you're solving a nonlinear high-dimensional OD. And apart from that, when you have two data points which are outside the injectivity radius of the score function, so essentially they lie in different charts, they lie on different charts, then in this case, you can also see that solving the OD is a very difficult problem. And the usual behavior that we have seen is that the geodesic optimization hardly leaves the initialization in these cases. So you start from a linear interpolation as an initialization for the geodesic, and the optimization won't really leave from there. Like, it will just map some parts of the trajectory onto the tangent space, but then there will be some some linear paths that you cannot avoid. And this metric has been explored by Saito and Matsubara recently using diffusion models, and they have shown some promising results. But we've also done independent research on this, and we've seen that it does seem to be working well for like local properties, but not for global properties. So in this work, we are trying to take a step towards towards creating a Riemannian construction that can give us global properties, or at least making the first steps in that direction. In this work, we make the assumption that the data distribution scales as the exponential of negative psi composed with phi, where psi is a strongly convex function and phi is a diffeomorphism. To give you some geometrical intuition, this kind of means that we are interested in distributions that are supported on a manifold that has a single chart, has a global chart, and at the same time, the distribution supported on this manifold is unimodal. Like this is more or less what this assumption means geometrically. So that it is a bit limited assumption, but we have to start from the basic cases, and trying to build up from that. For this class of distributions in this paper, we show how one can extract global geometry very efficiently, actually in closed form. If we use the pullback metric defined by the function f, shown up there as the gradient of psi composed with phi, then we can prove that this pullback metric construction enables the computation of the global geometry of the data. It gives closed form formulae for the distance function, the geodesic, the exponential, and other manifold maps. But I think an extra assumption that we make in order to be able to get closed form formulae is that psi is a strongly is a quadratic potential, which is also a convenient assumption to make for the training of the system. So we make the assumption it is x transpose times A inverse times x, where A is an SPD, and usually the matrix A is just parameterized by positive entries in the diagonal, and everything else is 0. In the paper we also prove that this construction satisfies strong geodesic convexity, which essentially means that the geodesics that you compute under this construction of the pullback metric will always lie in higher density paths than the endpoints. So you have two endpoints and you are trying to compute the geodesic. the geodesic that you are going to compute using the construction of this metric will pass through a region that will have higher likelihood than the endpoints. It is essentially concave. This function is concave. And interestingly, the construction that we are making is the construction of the pullback metric that we are proposing ends up being the same as the pullback metric of the score function if we regularize phi to be close to a local L2 isometry on the data support. Essentially, if you regularize the Jacobian of phi to be close to an orthogonal transformation, then our pullback construction and the construction of the pullback metric of the score function are the same, which is good because it means that the metric that we propose inherits all the good properties of the Jacobian of the score function that I discussed previously. And that is the derivation that describes why. Yeah, and that's why we call this construction score-based pullback Riemannian geometry. So, but I need to describe exactly how we train this. How we train the system is with normalizing flows. And normalizing flows are essentially invertible neural networks that map data from the data space to a latent space that has the same dimension as your ambient space. And in standard normalizing flows, we make the assumption that the distribution under the transformation is a Gaussian distribution where the covariance of the distribution is just identity. But in our construction, the function phi that I described previously is the function phi that I described previously is the normalizing flow. We parameterize this with a normalizing flow, and as I said, psi is a quadratic potential. So this means that if A is just the identity, then this whole construction is the same thing as a normalizing flow, essentially, more or less. But in our case, we're essentially training a normalizing flow where we're learning both the invertible transformation and the base distribution. We just allow the variance of every dimension of the latent space to be learnable. So some of them can actually be shut down, some of them can be collapsed. This is how we train the system. And let me explain that first, and then I will go to the Riemannian autoencoder. So yes, that is how you parameterize a normalizing flow. Phi is the normalizing flow, and this is the likelihood under the base distribution. So the deviation is that we allow for anisotropy and learning of the base distribution, and at the same time, we regularize phi to be close to a local isometry, so that our pullback metric construction can align with the pullback metric of the score function. And it turns out that once you train the system using the negative log likelihood data fitting term and the isometry preservation term, this term here regularizes phi to be close to a local isometry, which means that the Jacobian of the transformation is an orthogonal matrix. And this term is a volumetric term that just makes sure that the normalizing flow parametrization aligns perfectly without parametrization. Once you train the system like that, what ends up happening is that if you have a k-dimensional manifold, the normalizing flow is going to adapt to that. And it is going to adapt in the following way. You will see that the learnable variances in the latent space will exactly show you the dimension of the data manifold. So you have a k-dimensional data manifold. Only k of the variance values are going to be large, and everything else is going to shut down. It's going to go almost to zero. And by training the system in this way, you are essentially creating a latent space which is isometric to the data manifold. And it is also constructing an interpretable latent space. And essentially, it transforms the normalizing flow to a Riemannian autoencoder because it automatically detects the intrinsic dimension of the data, and at the same time, it gives you a chart. It gives you an encoder to that space and a decoder. And that is how you're constructing the Riemannian autoencoder after you train the framework. You can literally get a data point, map it to the latent space, and you will see that you're going to get a lot of zeros. So a lot of the dimensions will just be zeros because the variance learned there is going to be very small. So you can literally discard those dimensions, keep only the values that are non-zero, essentially, like that. And then when you want to decode, you literally just pad everything else. Like you can pad the redundant dimensions with zero and then decode. And that gives you a way to automatically detect the intrinsic dimension and find a map to that dimension. And apart from that, so it gives you two things. It gives you a way for this class of distributions to extract the geometry. You can extract the geodesics, the exponential map, and many other geometric properties. And simultaneously, it also gives you the chart of the manifold, which is essentially the encoder and the decoder to the intrinsic dimension of the manifold. And before I close, let me show you some results. So in this case, we trained the method on 3 manifolds again of 20, 50, and 100 dimensions that satisfy the distributional assumptions made earlier. And what we see here is the reconstruction error on the bottom as you increase the number of dimensions in the latent space. And and then up here you see the normalized cumulative learned variance. So this is literally, you start by plotting the kth most important, like basically just the cumulative sum of the k most important variances over the total variance of your latent space. And you can see that there is perfect alignment with the learned variance and the reconstruction error, which means that as soon as you add like 99% of the important dimensions based on your learned variance values, the reconstruction error goes almost to zero, which shows that the rest of the dimensions are redundant and the model has captured that. And these are results on MNIST, where on the left you see the real digits, and in this column you see the reconstructions when we use the first 176 important latent dimensions as found by the model. Then in the second one we use 200, then in the third one we use 271, and once you add 271, like the reconstruction is essentially perfect. And finally, these are some results on how the model does interpolation, which is computation of geodesics between 2 data points of the manifold. Here is in the case where we train only on the digit 1, and in this case we train on all the digits. And in this case we should have perfect performance, because this case doesn't really align perfectly with the unimodal assumption that we made. But we see that even in these cases, the geodesics tend to be same, but obviously can be improved if we generalize the framework even more. And this is direction for future work. In future work, we are considering extending the framework to a family of densities of this form, which are essentially mixtures of the distribution family that we considered in this work. And you can also use like more expressive diffeomorphisms and so on.
So let's just thank Georgo. Are there any questions? So, Lucas,
to learn the density of the target distribution. But then, is there a way to sample from it, except for like MCMC style?
Yes, because in this case, we learn the density using a normalizing flow, which means a normalizing flow is an invertible neural network. So essentially, if it is trained well, you will see that it will map the data distribution to the base distribution, which is going to be a Gaussian distribution. So if you want to generate samples, you just start by summing from the base distribution and then inverting the invertible function.
But then you need to learn both the inverse and the...
No, in this case, when you train normalizing flows are invertible neural networks in the sense, but they're also analytically invertible. We know the inverse analytically by construction. That's how we construct the layers of the network. So,
I really like this work, so please take that as given. I had two questions. One was, in your isotropic regularization, why do you think that it's good to move towards an isotropic L2 distance? If you're looking at images, often we'd think some sort of transport distance would be at least as natural. So have you thought about using that type of metric as a regularizer rather than simply an L2 distance?
let's look at this carefully. Yeah. So you're talking about the training objective. Yeah, I didn't spend a lot of time on that. So yeah, it's good to, yeah, please, could you?
It seems you're regularizing
Towards saying, at least locally, I want this to look like L2.
Yes.
And I'm just wondering why that's the most natural choice. Given if I take an image and shift it over by 3 pixels, that's not L2 close, but it is very transport close and would seem more natural to me.
We are regularizing the Jacobian of the transformation to be close to an orthogonal matrix. So it is locally an isometry, and because it is we're regularizing for local isometry, and this function is bijective by construction. So this will turn this into a global isometry, or approximately. This will happen approximately. Obviously, you won't get a perfect global isometry, but I think basically this tells this comes out from the mathematical analysis as well. Like we have seen that, yeah, there were some things that I haven't discussed. For example, that one.
But it's
that is basically this is an error bound on the reconstruction error of the Riemannian autoencoder, and it turns out that the error bound depends on this parameter C phi heavily, and this scalar C phi essentially quantifies how far phi is from a local L2 isometry. Yes, and yeah, maybe you can improve it, but yeah, I think this should be good enough to do the job.
So Georgios, my job as the chair is to make sure that no one falls asleep. But maybe one final question.
So if I understand your response correctly, you're saying basically I'm not doing L2 on the images, right? I'm doing L2 on some...
On the exponent, exponential term, right?
Yeah.
You do L2 on the exponent. Your Gibbs same way, right? You don't do L2 on the...
And then on Jacobians or something like this. So far from just naively thinking about L2
the log of
images.
that.
Yeah, I mean it is. I don't know what you mean by L2 now. I think I'm a bit confused because I'm tired. But let's discuss this again. So you mean here in this penalty term, right?
Yeah.
So this is just regularizing the flow to be close to a local isometry in the sense that locally it preserves lengths and angles. And I mean, intuitively why this is needed is to align the latent space structure with your data space. It creates a latent space which is going to be approximately isometric to the data space, and that is why you have the collapse of the redundant latent dimensions.
One final question.
It can be potentially improved, of course, but yeah,
So
it seems to be good enough.
One final question before we... Let us thank you, Georgios, one more time. Thank you.